Hello and welcome. Today we're going to explore a fascinating intersection of material science, advanced manufacturing, and artificial intelligence. We'll be looking at how we can create a new generation of products using renewable and bio-based materials, and how AI and machine learning are making this process faster, more economical, and far more sustainable than ever before.
The central idea is this. We can move beyond traditional manufacturing by using first-principle-based artificial intelligence and machine learning models to guide our processes. This isn't just about improving profitability for industries. It's about a fundamental shift towards optimizing our systems to reduce waste, lower energy consumption, and cut down on gas emissions. At the heart of this shift are two key technologies: additive manufacturing, which you probably know as 3D printing, and AI-directed automated laboratories. When we use 3D printing to create durable, sustainable materials, we open the door to high-value reuse and a more robust circular economy. By applying AI and machine learning workflows at every level of this process, we can achieve a new standard for developing and using bio-based and renewable materials.
Let's begin by setting the stage with the world of polymer materials. Polymers are everywhere. They are used in countless manufacturing methods, from molding and thermoforming to creating the plastic films used in packaging. Commodity polymers, like polyolefins and polyesters, dominate consumer products, the automotive industry, aerospace, and more. They offer huge advantages. They are relatively low cost, provide incredible design flexibility, are lightweight, and can be produced in high volumes. But there's a well-known problem: a lack of recyclability and circularity. For years, the goal has been to upcycle these materials, but significant commercial breakthroughs have been few, and environmental concerns are mounting. This challenge, however, presents a huge opportunity. The limitations of traditional petroleum-based polymers create a space to advance a circular economy, built on a new class of materials. The main goal of the work we are discussing today is to chart a course for this new reality, leveraging sustainable and renewable polymer materials by using the latest advances in discovery science and advanced manufacturing tools. The biodegradable nature of natural polymers and fibers can sometimes be seen as a weakness, but it can also be a challenge to be overcome through innovation. This is where artificial intelligence and machine learning, or AI/ML, come in. They are poised to dramatically accelerate the research and development of these new materials and the manufacturing processes that use them. To visualize how this works, consider the concept of a digital twin. Imagine a perfect virtual replica of a physical manufacturing system: a robot, a production line, the material itself. This digital model is fed real-time data from sensors in the physical world. An AI can then analyze this data, run simulations on the digital twin to predict outcomes, and make decisions that are sent back to guide the physical system. This creates a powerful feedback loop where the virtual world helps to intelligently guide and optimize the real world. Now, let's focus on the manufacturing method at the center of this revolution: additive manufacturing, or AM. AM, also known as 3D printing, is a process driven by mechatronics that builds three-dimensional objects layer by layer directly from a computer-aided design, or CAD model. Unlike traditional subtractive manufacturing, where you start with a block of material and carve away what you don't need, AM is additive. It only adds material where it's required. This process can use various raw materials, from powders and meltable filaments to viscoelastic materials and photocurable resins. The choice of material and method determines the form factor and function of the final object. While AM is used for metals, ceramics, and other materials, our focus here is on polymers, and specifically bio-based renewable materials. A wide array of materials, including thermoplastics, nanocomposites, and sustainable bio-based powders and fibers, have been developed to improve printability and performance for industries from aerospace and electronics to automotive and biomedical sectors. To understand this better, let's look at some of the most popular 3D printing techniques. First, there's fused deposition modeling, or FDM. This is probably what most people picture when they think of 3D printing. A filament of thermoplastic material is heated and extruded through a nozzle, building an object layer by layer on a heated bed. Next are the resin-based methods. Stereolithography, or SLA, uses an ultraviolet laser to precisely cure a liquid photopolymer resin in a vat, solidifying it layer by layer as a build platform moves.
Digital light projection, or DLP, is similar, but instead of a laser point, it uses a digital projector to flash an entire layer's image at once, which can make it faster. Then there's selective laser sintering, or SLS. This method uses a laser to sinter, or fuse together, powdered material, like thermoplastics or even composites, layer by layer in a powder bed. Finally, there's polyjet, or polymer jetting. This works much like an inkjet printer, where a printhead jets tiny droplets of liquid photopolymer onto a build tray. An ultraviolet lamp cures these droplets instantly. This method is known for creating parts with extremely high resolution and can even combine different materials and colors in a single print. Another important technique, not pictured here but similar in principle to FDM, is direct ink writing, or DIW. Instead of a solid filament, DIW extrudes a gel or liquid-like ink, which allows for an exceptionally wide range of materials to be used. Of course, each of these technologies comes with its own set of strengths and limitations. FDM is very low cost and robust, but can suffer from visible layer lines and has moderate precision. SLA offers high accuracy and an excellent surface finish, but the material choices are more limited. DLP is faster than SLA, but has similar material limitations. SLS can produce parts with excellent mechanical properties from a range of thermoplastics and composites, but the process can be expensive, and working with fine powders presents a safety hazard. Polyjet offers very high resolution and can print with multiple materials, but it is an expensive technology. And DIW can print with an exceptionally wide range of materials, but is sensitive to the material's viscosity. The cost for these systems can range from a few $100s for a hobbyist FDM printer to $500,000 or more for an industrial polyjet system. In summary, additive manufacturing has truly revolutionized how we can produce polymer parts, enabling higher performance and more complex geometries than ever before. While conventional manufacturing is still the go-to for massive scale-up, AM provides unparalleled freedom of form and rapid prototyping, which is crucial for improving time to market and addressing demanding applications where sustainability and waste reduction are key concerns. This technological shift in manufacturing doesn't exist in a vacuum. It's part of a larger industrial evolution. For the last decade, the concept of Industry 4.0 has been setting expectations for the future. Industry 4.0 is built on pillars like automation, digitization, and intelligent, autonomous systems. It envisions smart factories, where technologies like 3D printing, cyber-physical systems, cloud computing, and AI all work together in a digitally transformed industrial environment. But we are already looking ahead to the next step, Industry 5.0. This next evolution builds on the technologies of Industry 4.0, but shifts the focus to be more human-centric, sustainable, and resilient. It emphasizes collaboration between humans and robots, the use of ethical AI for personalized production, a strong focus on reducing environmental impact, and creating resilient value chains. The goal is to move beyond pure automation to empower workers, aligning technology with societal well-being and ecological goals. It's within this framework of Industry 4.0 and 5.0 that the case for renewable materials and additive manufacturing becomes so powerful. As manufacturers adapt to digital advancements and increasing regulations, the human in the loop remains essential, guiding these powerful new tools toward more agile and environmentally conscious outcomes. Because of its digital and additive nature, 3D printing is a unique, promising technology for building a circular economy. It offers wide-ranging opportunities to produce customized, on-demand products. This eliminates the need for large unsold inventories and reduces overall waste. This on-demand production saves materials and resources, leading to more sustainable output. It's not just about preventing material loss during fabrication, it's about fundamentally rethinking the supply chain. Additive manufacturing can adopt a more circular production approach by using bio-based, renewable, recycled, and upcycled materials as its inputs. Because materials are only added where needed, the process is inherently less wasteful. To truly transition towards a circular economy using 3D printing, a few things are critical. We need to increase our knowledge of how to design products specifically for circularity. We need an organizational shift in supply chains to prioritize localized and recycled materials. We need to develop new genomes of materials designed for upcyclability. And finally, we need to train a skilled workforce of scientists and technicians in this new sustainable materials economy. This brings us to the core of our discussion, the materials themselves. There is a strong and growing interest in using bio-based materials for 3D printing. These materials are attractive because they come from sustainable and renewable resources. Examples include polylactic acid, or PLA, which is derived from fermented corn or sugarcane. There are also polysaccharides like cellulose from wood pulp, starch, and chitosan from crustacean shells. We also see interest in polyhydroxyalkanoates, or PHAs, which are biodegradable polymers produced by microorganisms. These natural polymers offer a clear pathway to circularity, sustainability, and biodegradability. We can group them by their origin. Plant-based polymers include cellulose, starch, and natural rubber. Animal-based polymers include collagen, keratin, and chitin. And microbial-based polymers include PHAs and bacterial cellulose. Each of these has a unique chemical structure that offers different properties.
However, working with these materials presents a challenge. Many 3D printing methods, especially extrusion-based ones like FDM and DIW, require specific viscoelastic properties or melt behavior. Bio-based materials often demonstrate lower thermal stability and poorer mechanical performance compared to their synthetic petroleum-based counterparts. Their processing can be difficult, as they may degrade or char at high temperatures. To overcome these limitations, researchers are exploring several strategies. These include chemical modification of the polymers, blending them with more robust synthetic polymers, or incorporating filler materials to reinforce them. For example, PLA is a popular material, but it can be formulated with additives to improve its properties. PHAs offer even better biodegradability than PLA and are a promising material for the future. Other materials, like wood plant composites, blend bio-based fibers with synthetic polymers to create printable filaments. We are also seeing a rise in bio-based resins and hydrogels for resin-based printing methods like SLA and DLP. Hydrogels made from materials like alginate or gelatin can be used in extrusion printing if they have the right properties, like shear thinning behavior and a sufficient yield stress. This is an active area of research. For instance, studies have shown successful 3D printing of a blended material of thermopolyurethane, TPU, and polylactic acid, PLA. By itself, this blend is a thermomechanically robust material. But with the addition of a small amount of graphene oxide, the resulting nanocomposite becomes a superior material with biocompatible features. Other work has demonstrated the 3D printing of a nanocellulose composite hydrogel using SLA, creating materials with enhanced properties suitable for biomedical engineering. Researchers have also improved the properties of 3D printed polymethylacrylate composites by adding surfactant-modified chitosan particles, which improves thermomechanical properties. Even adding a tiny amount of chitin nanowhiskers, as little as 0.5% by weight, to a methylacrylate resin has been shown to enhance tensile strength, strain at break, and thermal degradation temperatures for the final nanocomposite. Of course, the biodegradability of these materials, while an advantage for sustainability, can be a challenge if the product needs to be durable. The advantages of renewable sourcing can also be offset by higher costs, often due to the purification steps required, or a lack of quality control. Natural fibers like hemp, jute, and flax can be used as reinforcements to improve strength and stiffness in composites with thermoplastics like PLA or propylene. However, these bio-based fibers often face challenges with moisture absorption and can have varying quality, which complicates processing. Despite these challenges, the advantages of natural polymers and fiber blends for 3D printing are very promising. Future research must focus on developing more advanced composite bioinks that synergistically combine natural polymers, synthetic polymers, and nanoparticles to achieve the optimal balance of printability, mechanical properties, and degradation. The intrinsic properties of these materials are a huge advantage. They are sustainable, biodegradable, often biocompatible, and can be less toxic to work with. Ultimately, to enhance the printability, mechanical properties, and functionality of these natural polymer composites for 3D printing, we will need more AI and machine learning-driven workflows. This is where we bring everything together. With the recent advances in 3D printing, there is a strong interest in incorporating AI, ML-driven workflows across the entire process, from concept and design all the way through manufacturing. These workflows will be essential for developing new 3D printing materials, creating new protocols, and even designing new machines. In-situ, real-time sensors can provide a constant feedback loop for monitoring and control during the printing process. For developing new polymer composites, a concept called the self-driving laboratory will become a key tool for high-throughput experimentation. The goal is to achieve faster and better correlations between a material's structure, composition, processing, and its final properties. For 3D printing, optimization will lead to higher resolution, faster speeds, and a broader range of materials for demanding applications. To understand how AI/ML can be applied, Let's break down the different methods. We can broadly categorize machine learning approaches into supervised learning and unsupervised learning. Supervised learning is used when we have labeled data and we want to train a model to make predictions. In biopolymer production, we might use linear regression to predict the yield or molecular weight of a polymer. We could use random forest models to improve accuracy and reduce overfitting. Neural networks can predict complex non-linear processes, and support vector machines can be used to classify outcomes, for example, whether a particular formulation will succeed or fail. Unsupervised learning, on the other hand, is used when we don't have labeled data, and the goal is to find hidden patterns or structures within the data itself. For example, under the umbrella of clustering algorithms, we could use k-means to categorize raw materials based on their quality, or use hierarchical clustering to group similar microbial strains. In dimensionality reduction, techniques like PCA can identify the key factors affecting process variability. Anomaly detection algorithms like isolation forest can detect outliers in raw material quality or identify abnormal behavior during a fermentation process. And finally, association rule learning can be used to discover relationships between different components, for instance, finding frequent combinations of materials that lead to desirable properties. Going a level deeper, we can look at the specific architectures used in deep learning. Neural networks and deep learning are particularly powerful for these complex tasks. Multi-layer perceptrons, MLPs, can be used to predict fermentation outcomes or optimize nutrient supply schedules. Convolutional neural networks, CNNs, which are excellent at processing image data, can be used to analyze microscopic images of materials to automatically detect defects in biopolymers. Recurrent neural networks, RNNs, are designed for sequential data, making them ideal for modeling the dynamics of a process over time. Generative adversarial networks, GANs, can even simulate production scenarios and generate synthetic data for testing, which is incredibly useful when real-world data is scarce. When we approach new materials with these AI/ML tools, it's essential to design them for manufacturability right from the outset. To achieve an optimal polymer design with the right molecular weight, melting point, and branching architecture for good properties and processability traditionally requires a huge number of experiments. AI/ML can dramatically accelerate this by connecting the desired polymer properties with the intended 3D printing method from the very beginning. By starting with a good simulation, perhaps even guided by a large language model, it's possible to augment the development of automated systems like self-driving labs. Let's look at how these ML and DL applications compare across the different stages of production. First, in polymer design, the objective is to discover brand new polymers with specific target properties. The bottleneck here is that we often have only small, heterogeneous datasets to work with. The inputs to the model are things like molecular structure and composition. The labels, or what we are trying to predict, are properties like glass transition temperature, modulus, or biocompatibility. The ML tools used here include random forest, gradient boost, and advanced inverse design frameworks that work backward from a desired property to suggest a molecular structure. Next, in polymer processing, like continuous extrusion or molding, the objective is to optimize the manufacturing process. The bottleneck is the need for high-quality labeled data and robust sensor integration. The inputs are machine settings, data from sensors over time, and material grades. The labels are measures of quality, such as dimensional accuracy, surface quality, and defect rates. Here, the ML tools might be regressors built on neural networks or physics-informed neural networks that incorporate known physical laws into the model. Finally, in 3D and 4D printing, the objective is to achieve accurate, defect-free printed parts, and in the case of 4D printing, parts that can change shape or function over time in response to a stimulus. The major bottleneck is coupling and interpreting multimodal data from different sources, like material information, the G-code instructions for the printer, in-situ images, and other sensor signals. The inputs are the material formulation, print parameters, and geometry. The labels are things like printability scores, the presence of defects or porosity, and the final mechanical or biological performance. The tools for this are highly specialized: artificial neural networks designed for printability, CNNs or vision transformers for image analysis, Bayesian optimization for fine-tuning parameters, and reinforcement learning, where an AI agent learns the optimal printing strategy through trial and error. This leads us to the concept of the self-driving laboratory, or SDL. This represents a significant advance in how chemical and material synthesis is done. In an SDL, instead of a human operator performing every step of synthesizing, characterizing, and analyzing a material, these steps are automated. The crucial decision-making within this workflow is handled by machine learning-driven algorithms that suggest the next set of experimental parameters to best optimize the material or molecule. The role of the human expert is not obsolete here. In fact, it's more important than ever. The expert's job is to define the scientific questions, constrain the parameter space, determine the appropriate reaction protocols, and provide oversight. We can explore the development of new bio-based materials for 3D printing using an SDL built around continuous flow reaction chemistry. This allows for precise control over parameters like composition, flow rate, pressure, and temperature. The reactions can be monitored in real time using analytical instruments like infrared or Raman spectroscopy. This data feeds back to the AI model, creating a continuous feedback loop. The SDL becomes a real-time, autonomous system for data collection and training, generating massive amounts of clean, high-quality data that can be used to build even more powerful models. This SDL concept can also be applied directly to the 3D printing process itself. An SDL for 3D printing would use real-time methods to detect residual stress or defects, monitor changes in viscosity, and automatically adjust heating or photocuring parameters on the fly. With a feedback loop to correct defects during the print, an optimal process is realized with each and every part. The challenge is to design these systems with the right sensors, computational resources, and mechatronics to enable fully autonomous operation. So, in conclusion, what is the outlook? AI and machine learning have vast potential to explore the enormous number of parameters involved in synthesizing new polymers and optimizing 3D printing processes. Based on available data, AI/ML can effectively optimize both material synthesis and the printing process itself, helping to develop new bio-based and renewable polymers. This automates the path to informed decision-making, resulting in greater efficiency and faster development. The benefits are numerous. They include the creation of new high-performance materials, enhanced optimization of recipes and processes, more efficient quality control, and automated design and functionality development. This path should lead to higher throughput experimentation and a more economical integration of these advanced technologies, pushing us forward into the new industrial paradigms of Industry 4.0 and 5.0. It is a vision for a future of manufacturing that is not only more advanced, but also fundamentally more sustainable. Thank you.